two pattern, two set of the thin coating, photolithography, and etching. And you can finish the geometry, the painting. Okay, so here's a planar motion about this arrow, about 20 micrometers. The temperature increase is about 600 degrees C. 600 degrees C. Comparable to the results of Professor Gakko in 1992. But the one advantage is no more using the Liga process. We use the ordinary clean room and the surface micromachining. We can finish this kind of process. So the achievement, we can make it easier. We can make it easier. We're using the easier machine. This kind of thermal actuator not stop over there, because one drawback show up. Okay, the action, the thermal actuator action always point downward, only downward. It is possible upward. If it possible like upward, we need a two-way actuation. Right? In ordinary manner for my hand, I can point to the right, I can point to the left. I can rotate counterclockwise or counterclockwise. Correct? So we need two direction actuation, not only one direction. The previous finding is only one way actuation. We need two way. How do we make the two way? This one. In 2001, Professor Professor Wang found in the National Tsinghua University, also in the Hsinchu. He also used the second surface micromachining to provide you with two-way actuator. But in design, it's a little bit complex. He used two pairs of heating beams. You can see 4 beams right now. 4 beams. There is an outer beam. One pair the outer beam. One pair the inner beams. Outer beams is used for what? Outer beams is used for your downward actuator. Inner beam is for your upward actuator. Why can he create such an action, two-way action? Because we're using some non-symmetric structure. Meaning that these four bars or 4 beams are not on the same plane. Not on the same plane. They have a different height, different plane height. If you look at the inner one, there is a small step. Meaning that the inner fingers is the lower press. So if you're hitting inner one, right? If you're hitting the inner one, you can feel a tendency trying to push the structure upward. Inner heating, outer ring, no heating. Only one pair the beams are heating. So when you do the inner beam, these two points, this point and then that point is the inner beam or this inner beam. When you get it perform, you have the deformation and try to push the beam forward, but you cannot forward, right? Fix at the end point fix. So no way to do, only up to the sky, upward to the sky. So right now is the only time. So we should wait it, wait a little bit for the So for the inner beam, the outer beam is the inner beam. Is the inner beam. Inner, outer. So inner beam will induce upward force, upward motion, upward motion, outer beam will generate downward motion, downward motion. I cannot wait too long. I just tell you. I continue to talk about that. You mean that, there is no free lunch. There is no free lunch in the world. You have only one pair of beams. You can do only one way the action. You want to two-way the action, you need two pairs of beams. Two pairs of beams. So you mean there is no free lunch. You want more function, you must make your system more complex. So more complex, right? Two pairs. So one pair is responsible for upward. Another one is for downward. So this is the bi-direction thermo actuator. But whatever liga, whatever the only one pair the silicon micro machine beams. Here is a two-layer silicon micro machine. All these three configurations have the problem. What problem? The temperature is too hot. We have not mentioned about the temperature. We just say heating. Just heating. Okay, heating. You want to heat it until to the point that it starting we have the buckle micro machine. Buckle micro machine. Micro unique is to how high? At least 400 or 500 degrees C. Or even for this case, you can see 1,000 degrees C. Or even 1,300. You know how high is it? What is the melting point of the silicon? Melting point of the silicon is 1,450. 4,50 degrees C. So just a little bit lower than the melting point. Little bit lower than the melting point of silicon. So I ever show the presentation to Professor Feng. He showed us the actuation video. We can see there is a very hot angle. The original color of the silicon is gray, like the silver color. But his device is red. Red color means hot, very hot. It's something like the steel heating up to the 1,000 degrees C. Much red and hot, right? So look at that. You mean that, okay, you can do this kind of action, but it is, it's good for our commercialization. It's good for our commercialization. Not true, right? Our commercialization should be, okay, with temperature very high. We try to make our working temperature as low as possible. 1,000 is not worth for our real application. Right? If you want to use this kind of thermo actuator to push in other object, before it start to move, it has to be cooked. 1000 degrees C, right? You do the cooking or pushing. It's something like the cooking. Right? 1000 degrees C is too high. So it's a problem. So how to decrease the working temperature is the issue. How to decrease the working frequency is the issue. So if you regard the thermal expansion here, right? The reason why we increase delta T up to 1000 degrees C is because our thermal expansion coefficient may be too small. Whatever metal or silicon, they have the value about this 3 to 5 ppm per degree C. Small. So you need to increase your temperature 1000 degrees C. Then you can have your total delta L over L equal to 3 to 5 divided by 1000. It means about 0.3%. 0.3 to 0.5% of the overall length. This kind of length may be enough for us to initiate a buckle, a parent buckle. But because 1000 degrees C is so high, we have an idea. What idea? Can we use low temperature? Low temperature is good, right? So why not? Or my thinking is, why not use plastic? Why not use the plastic material to do the thermal actuator? Because plastic material has a thermal expansion 10 times larger than the silicon or metal. It means that we only increase to 100 degrees C and enough for our actuation. 100 degrees C is okay, right? It's not so high. When cooling, something like the water boiling temperature. It's not very high. So in the last moment, we try to use different materials. To take the press, we use the plastic to replace the metal or silicon about our thermal actuator. So it's our thinking. It's our thinking way. We try to use one kind of plastic. We call it the parylene. Parylene, I can not yet talk about that in the manner of plastic. Very similar to your plastic bag. Your plastic bag is plastic, right? Right now in our daily life, many stuff are plastic, right? Many stuff is plastic. The plate above is plastic, right? Maybe some floor are plastic, right? Many partition materials are plastic, right? Even your shoe may be plastic, right? Many stuff is plastic. Plastic has the characteristic is what? Very cheap, right? Very cheap, and the density very close to water. Density about what? Very close, very light, cheap, and most of all is what? Thermal expansion coefficient is big. It's very big. So if we can increase the temperature of plastics, you can easily initiate a buckling phenomenon. You can easily induce a buckling phenomenon. So here we try to use this kind of method to make a thermal buckle actuator here. Either designed by our university. What is it? We try to make a pump. We try to make a pump with a membrane. We hope this membrane can compress the liquid inside. We can compress the liquid. What, to one direction? We do the squeezing. We hope to do the squeezing, water squeezing. So before squeezing, you need need let your membrane have the vertical, right? Vertical deformation. Actually, the vertical buckling. We hope to generate buckling motion. So our design is different from the previous one. We directly have this kind of idea. The center part, you can see this is a chamber. This is a chamber. And the flow channel flow inside this chamber. And if you can let your membrane upward, you can let the liquid flow inside. And then we push down, you will squeeze out. You squeeze out. So it's very similar to our heart structure. Our heart. Right? Squeeze, right? Make it larger. Suction in the air at the blood and squeeze it, push out. Of course, our heart has not only the pump, we also have one pair of check valve. Understand? Valve. So pump and valve. So valve pump is initiating the flow. Initiate the flow. Valve is trying to unify one direction. Only one direction. We try to unify one direction pumping only. So this is our design. Our design is quite different from the cantilever beam in the before case. The case we mentioned before. Little bit different. I can explain more. Here, all this stuff, parylene is the kind of plastic. And how to make it heat it up? We need embed heating electrode inside. We embed the heating electrode inside. So we do the heating about the resistor. The heat will diffuse into the plastic to cause a thermal expansion. So this geometry, we need to make it I introduce the processes, but first you can understand it. First of all, have some parylene and the bonded layer. Then we use the photoresist and our sacrificial layer. Then we constructed our pumping chamber. So this layer is also the parylene. This is the second layer of the parylene. Second layer of the plastic. Okay, after complete about the chamber structure, the next step we want to do the heater. So here we put in some heating metal here, the metal, and it's the output and the in and out, resistor in and out. This is the resistor, then the in and out are two electrodes. Not only that, we keep doing the top layer, parylene layer, the third layer. So we coat it several times the polymer, try to coat it, exactly coating the heater, So finally, finish. We try to remove the sacrificial layer. So finally, you will divide the hollow. It's a hollow chamber and hollow micro channel. You can let the flow inside, liquid flow inside. And we start to do the excitation. So the membrane will start to up and down, up and down, up and down, up and down. And the reason why it can up and down is because here, this design is very similar, actually very similar to our previous case about what? With the previous case, though, it's longer and shorter, and it's a thinner and wider, right? So here, try to make something different. Here, above this heater, the lower layer is thinner. The upper layer is thicker. So when do the heating, top layer, we are feeding less heating, feeding very less the heating. And the lower case, we feel large sense of heating, large deformation, large deformation. So finally, you will find a large deformation into small deformation. So this film will go down, a little bit downward. It induces a buckling phenomena similar to this or this. Buckle out, downward. So this is the process for our thermo actuating micro pump. So it's a finished device. This is a finished device. Heater. And it's a hollow chamber. Heater. Channel in and out. In global picture like this. So you can see this white dot. This white dot is this overall chamber. It's this pump. So along the long channel, this is the overall channel. We install two pumps. One pump and another pump. And this is a pad for each pump. One pump has two electrodes. One pump has two electrodes. So you can control the sequence. So these two pumps try to pump in together or in a cascading way, you can cooperate. And try to push the flow from this entrance region to the exit region. So this is a parylene thermo actuating device we can ever use in our study. 3 micrometer thick parylene member. This member is 3 microns. Only 3 microns. And the resistor is 100 ohm resistor. We apply only 3 voltage. We can induce a 0.35 micron displacement. Of course, you see this is not a parallel. This is not a parallel. But we only use 3 volts. How about the case for the previous Johnson University and Tsinghua University? They apply hundreds of volts, 500 or 600 volts, very, very huge, very, very high. But for our case, only 3 volts. 3 volts. 3 volts means even for our general lithium battery, for our mobile, right? For mobile, lithium battery voltage is 3.7 volts, is a standard voltage supply. So we can use ordinary lithium battery to do the pushing. So it's compatible with our electronic device, our mobile, right? Many kinds of lithium battery. Lithium battery, remember, is 3.7. Right now it's standard voltage. Good enough for driving any kinds of electronics, IC, and so on. So we try to easy to drive our actuator. Low voltage, low temperature. But frequency is not so low. I can tell you later on. So we a little bit break, and I will tell you what the performance of the device. Okay? Not 10 minutes.